Right, okay, afternoon everybody. So, a fairly quick pass through all there is to data reduction in 40 odd minutes. Now those of you who are paying attention in the very end of Kyla's talk will have already learned something important. Namely, there is actually only one good looking galaxy in the universe. This is the, I don't think Kyla actually said the name of this galaxy, it's the wonderfully evocatively named NGC 1365, also the Great Barred Spiral Galaxy in Fornax. This talk is a talk I've given in the last two of these observational techniques workshops. It's been brought up to date a little bit, and all the jokes that didn't work in the last two have been taken out. Now, actually, I'm just kidding. I left them all in the hope of a more discerning audience, so you're all being judged. But now, so data reduction. Why is it called data reduction? Well, there's an awful lot of data, and it needs to be reduced. You've probably been subjected to a lot of this sort of data deluge stuff, but Hermes, when I first gave this talk, this was AAO. Hermes has twice as many detectors, and they're twice the size, so 64 megapixels altogether. Roughly speaking, you do 2 exposures, maybe 1 science frame, 1 arc in 30 minutes. It's about 1 gigabyte an hour. Interestingly, that's about that's about the same data rate as the old Iris-2 detector, which was only 1024 square and just 1 chip. But it was read out every 15 seconds. It also comes to about 1 gigabyte an hour. The saving grace with Iris-2 was that that data isn't actually all recorded. It's pre-processed by the data acquisition system. So there's a sort of data acquisition pipeline pre-processing the data. And although that's not a typical data reduction pipeline, we'll come back to pipelines later. To try and put this into some sort of context, gigabytes, etc., the complete works of Shakespeare, 5.5 megabytes per lifetime. That's very slightly less than the size of the JPEG used for this illustration, which is a photo of the front page of the first folio. Now, of course, that is actually just the published data. It doesn't include things like the rough draft, where Macbeth decides that knifing Duncan wouldn't go down well with the voters, and they all live happily ever after. It's also the case that Shakespeare had time to think about pretty much every word that goes in there. He goes, shall I compare thee to a summer's day? Will I compare? Oh gosh, which is it supposed to be? And it's different if you're American and British anyway. He could do that with the sort of data rates that we deal with. You can't look at every pixel, you can't even look at every spectrum, you can't look at anything some of the time. You're forced back onto automatic pipelines. If you really need decisions making on a lot of that stuff, you go put it out to things like Galaxy Zoo and so on. It's a lot of data to have to deal with. SkyMapper, 100 gigabytes an hour at its peak. ASCAP, when it comes on full line, 9 terabytes a second. That's 32 petabytes an hour. So we're now talking in prefixes that I never used to have to deal with. So what's a petabyte? Well, here's one way of looking at it. Voice recordings of all the phone calls made in the US in a year would be just under 300 petabytes. Now, of course, nobody's going to do that, of course. I mean, even the NSA isn't going to record all that. You know, the National Security doesn't need to do that sort of thing. So, you know, that's an artificial comparison. But you do need to know these things. So everybody go kilobyte, megabyte, gigabyte, terabyte, petabyte, exabyte, zettabyte, yottabyte, brontobyte. Okay, brontobyte is not made up. It might be slightly unofficial. You don't come across these very often. When I was putting the slide together, the only place I actually found yottabyte was in a discussion of, funnily enough, the National Security Agency's data center. But I wouldn't read anything into that. I'm making no comment. It's science. The point is not to collect data. Data is just something that fills your disks and gives trouble to the people who run the backup systems. The point is to understand the universe. What you're trying to do is turn all that data into something much, much smaller. 6 numbers, 1 number would be good, H0 to a decent figure. to get there, 3 questions which this talk is sort of about. One is, what do you need to do? What does the data reduction actually have to do? 2 is, who should do it? And that who should be you, so pay attention. It isn't necessarily you. If you're a student now, you'll appreciate that when you have students, it's going to be them instead. And it's also always possible that it's actually the observatory's job, which is something I'll come to later. And then, of course, there's how do you do it? In passing, if anybody's wondering about the bullet holes rather than bullet points, I did actually want to use real, actual bullet images when I set this up, but after about half an hour Googling for them, I suddenly remembered that the Department of Industry records all these, and possibly somewhere in Utah as well, so you're stuck with these. What needs to be done? Here's the universe waiting for you to study it. Your job is to understand it well enough that you can describe it to your next door neighbour. Okay, it's slightly out of date, but they're still being repeated. To do that, there's a lot of things get in the way. Here's the universe over here. There's photons come from that until they hit the atmosphere. The atmosphere messes things up. It's got emission lines, it's got absorption bands, it shimmers. Okay, it's got oxygen, so on balance, good, but it does mess up your data. It's a nice image. It's got no scientific content whatsoever, but I like the image. Here's a heap of presentations. If you've got no content, go for a good image. Remember that. Goes through the atmosphere. It lands on the end of your telescope. So photon comes down. Right. I don't use lasers. This is safe for jumbo jets. Here's the 2DF top-end ring. There are fibres all over this. If you're lucky, the light from the photons from your galaxy will come into the fibre that you positioned in exactly the right place for it. If not, it's had a billion-year journey for nothing, but those are the breaks. It goes down through the fibre to the instrument. The fibres have their own imperfections. They have distortions. They have all sorts of things that a fibre expert will tell you are wrong with fibres. Finally, it gets down to the spectrograph, and it goes. This is the Hermes spectrograph, and you can see that there's an awful lot of optical elements in there, and every single one of them has its own imperfections, distortions, etc. Finally, it hits the, well, actually it's not finally, there's more to come. It hits the detector. This is the Hermes detector, or one of the 4 Hermes detectors, 6 centimeters square, 16 megapixels, 50 micropixels, and obviously, as you've just had 45 minutes worth from Kyla, it's not actually perfect either. The way you make a perfect one of these is you make an awful lot of imperfect ones, test them, see which ones, and then sort them into really good, good enough for science, good enough for engineering, good for a stand on a trade show. So that's inputs. You're starting to get there, and then it goes through software. Now, you may have spotted a theme here, right? The photons are fine, but the atmosphere is not perfect. The fibres are not perfect. The spectrograph optics are not perfect. The detector is not perfect. But now we come to the software. Right. No, sorry. Some people are just naive. Yes, okay, audience participation. What is it? Fortran. Right, hey, good, right. So how many people have been taught Fortran? Oh, that's a pretty good, right. We've got an older audience than I thought. Or possibly people who do supercomputing, which is where most of it is now. Who's been taught C, C++, Python? I bet every hand. Not every hand, all right. Oh, it's a different distribution to... what was that? Oh, yeah, okay. I've written in RPG. P.O. Watman. This is a bit of the 2D FDR code. It's quite an, 2D FDR has its origins quite a long way back. You'll hear a lot more about 2D FDR later from people like Mike Birchall who are still writing in this. So, all the way through, here's the train that it all goes through, and you can see that there's a lot of things going to go wrong along the way. So I now wanted to have a look at some of the data, the actual data. This is clearly not data, this is absence of data, this is Hermes with the lens cap on. There's just nothing there. But if you imagined putting a fibre into the middle here, you might see that. Well, actually, of course, you don't see that because Hermes is a spectrograph, so what you actually see is the light spread out across in wavelength. If you were to put another fibre, you get another one up there, and if you were to put a third fibre in, you get one down there as well. And eventually, you put in 400 fibres, and it fills up the whole thing, all spread out from red to blue or blue to red. At first, we didn't actually know. There's a lot of optics. You never know quite which way you put the detector in. The first thing you have to do when you get a new instrument is actually work out which way round the light is. We got Hermes wrong. It took a while to work that one out. So, looking at just this one spectrum in the middle from the one fibre, I was lying, of course. It doesn't really go from blue to red the way I showed it. This is the blue detector, and it's therefore mostly blue. It covers about 200 angstroms, so it is mostly blue. But actually, I'm fibbing again because this is Hermes. It's not a colour detector. This is not your Nikon or Canon camera. This is not even your iPhone. Your iPhone can take colour photos, but Hermes can't. So it's grey, really, but of course. Grey is a boring colour to display things in, so people usually use a sort of false colour like this, where you just have, this is the heat spectrum used in IRAF, SkyCat has it as a default, I think. The more intense you've got, the brighter it is, and the more bright orange it is. Now, if you look at that closely, so I've just selected this now, and this is now showing the profile through it. You can see why people get interested, why people really like Spectra, I reckon. This is really nice. This is the sun. So this is from one of the early test images from Hermes. Here's H beta, 4851, 4860. Very quickly, H beta, 4860. 40. Yeah. And it depends on whether you're brought up in angstroms or nanometers, or it's half a micron if you work in the infrared, isn't it? Nearly. It's pretty. Now, of course, what you actually want, as Kai was saying, what you really want to know is you want to know what the actual wavelengths of all those points are, so you put an arc on instead. So here's an arc, deliberately brought up the contrast here so that you can see the continuum in the arc. You can see the main strong arc lines. You can see, and now you start seeing some of the things Kai was talking about. There are cosmic rays all over this. There are saturated pixels. Some of those saturated pixels are trailing in different directions. That's a complicated feature of the detector. If you home in on just the arc, there it is. So the job is to work out what these lines are, which turns out to be not all that straightforward because published lists of arc lines don't always agree about what the wavelengths are. But ideally, you work out what the pixel to wavelength, the pixel number to wavelength relation is. It's not linear in Hermes, it's pretty close to cubic, but it's of course a slightly different cubic depending on where you are on the instrument because of all the optical distortions, etc., etc. Now, if you look at, just home in on that arc line again, and That is supposed to be a moving. Oh.
I clicked it with the mouse.
No. Oh. So it thinks it's. Oh, well, that will cut down the talk slightly, so that saves that problem. What this does is it very nicely zooms in on one of those central lines. Up, okay, and shows you that one of those lines looks like this. So you've got, this is what you're seeing now. Ideally, you would see it's a single wavelength in a single place. You'd ideally see just a single spike in there. You don't. You see a profile. You see, what you're seeing here is the point spread function produced by the spectrograph. It smears it out. If you want to extract your data properly, you're going to want to know you're going to want to have fitted that point spread function to the data, and that point spread function varies depending on where you are on the chip as well, which is kind of annoying and takes a lot of time working out. But it's one of the things you have to do in order to extract your data properly. And of course, what you do is, it's not just one spectrum, it would be easy enough to extract one spectrum, but in fact 400 are squeezed onto this detector. You can see the 400 there. So here's the 400 in groups of 10. I've selected 2 groups of 10 there. The rule of optical design and instrument design is you squeeze as many fibres, as many spectra as possible into the available space on the detector, and then claim that software will be able to sort it all out afterwards. Sometimes it works. Here's just one clip through that. Another movie that isn't going to work. Well, I didn't expect it to after the first. Here's 2 of those groups of 10 fibres, and what this shows you is that not every fibre is created equal. You can see that there are fibres that are much weaker than the others. Their transmission is just down. It's pure coincidence. I think that the weak one is the 7th one from the left and from the right in each case. But that's the sort of problem you have to calibrate out. Anybody see what's wrong with the 10 fibres on the left here? Give you a clue. The 10 fibres on the left here. There's only 9. I actually don't know what happened to the missing fibre in this particular image. It's possible it's a broken fibre. You do get broken fibres, and you can't therefore rely on just counting all the way down and hoping that that tells you what object you've got, what fibre you're on. This shows the whole thing. I've just stretched the aspect ratio here to emphasise the curvature of the fibre, of the spectrum in each case. So what this shows you is you can't get away with just adding each cross-section along from here and clumping them all together, because that's just not going to work up here. You can also see, this shows you the profile of these 3 fibres. They're just starting to run into one another. If you were down here, they run into each other much more. That sort of thing has to be fitted, modelled, if you really want to get the best you possibly can out of this data. Here's a set of 5 of those groups of 10. This is the flat field, and this is what it looks like when you have an arc instead. And one thing I wanted to point out here is that if you look really closely, you'll see that the arcs are not in exactly the same position. It's not even a smooth transition as you go up. There are little discrete jumps in the wavelength as you go. In this case, that's mostly because of the position of the fibres on the slit. So because they're not perfectly aligned, there's a slight offset in the wavelengths. So there are all sorts of things waiting to catch you here. You really do have to fit every single arc individually. You have to extract every single arc spectrum individually, fit it, then apply that to the science data. Okay, here's the detector, just to emphasize what Kyla was saying. This is some early lab tests of the Hermes detector. It doesn't look too ununiform. You can see that there's a clear set of 4 quadrants because the detector is actually read out from 4 separate amplifiers at each corner of the chip. In practice, we only read out from 2, so that all of this, so generally all of one spectrum is read out by the same amplifier, which at least means you don't get a break in the middle of most spectra, but there is this discontinuity here. So the amplifiers have slightly different characteristics. If you look closely, you can also see that it's not actually completely flat in either of those. And if you really want to give yourself a scare, you can change the clipping of the display so that what you get is this. Don't be completely scared by that. Some of the uniformity there is because the flat field illumination isn't flat. That's one thing to remember. Flat fields are never actually flat. But the other is that the detector is not completely uniform. If you turn it over on it, if you turn that surface that you can see there over on its side, you can see that there are hot pixels that are slightly more responsive. If you turn this the other way up and look from the other side, there are actually dark pixels as well. So there are hot pixels and cool pixels. This is a top-notch detector, but when you look at it at this sort of this closely, you discover that it's not actually anything like perfect, which is what I'm trying to say. So these are what you've got to do. Or this is some of the things you've got to do. Detector effects, you've got to correct for nonlinearity, amplify again. You can read it as well as I can. You've got to find the spectra. Oh, this is actually an AAO spectra, and they go the other way in the image on this one. But the principle's the same. You locate them from the flat fields. You would run some sort of optimal extraction procedure. You subtract them, you get the wavelengths, you fit the arcs. You scrunch the spectra to a linear wavelength scale because that's much easier to deal with than trying to carry around the wavelength relationship as well all the time. Although you only want to scrunch something once if you can possibly avoid doing it more. So here you are. You've got lots of spectra. Universe spectra, nicely calibrated, wavelength fitted. Now it's up to you to turn them into science. This is not an astronomer asleep. This is not. These are individual. Those are Z's. These are redshifts. These are some of the numbers that you're trying to get out. Here's the fancy plot from the 2DF Galaxy Redshift survey. This is clearly science. Going for getting this out is basically a matter of getting the instrument out of the data. Somebody is a mistake. Oh, okay, all right. I've forgotten the sequence of my own talk. I was going to say, I said wavelength calibrated. We don't tend to do flux calibration. Flux calibration is tricky, and for a lot of things it's not needed. But this particular cautionary tale is from earlier in my career. Does anybody know where this is? Right. You're the first person in 3 years to get that. It's Burlington House. It's where the Royal Astronomical Society hold their meetings. And way back, not way back, sometime back when I was a student, I sat in a meeting here listening to somebody give a talk about an anomalous H-alpha H-beta ratio they'd found in a Seaford galaxy. And I was quite interested in this particular talk because I'd supplied him with the data. And as I sat there, I got this dreadful feeling of horror crept over me as I realised that he hadn't realised that the data wasn't flux calibrated and that his anomalous H-alpha H-beta ratio was in fact the response curve of our detector. You don't want to do that in front of the Royal Astronomical Society. I'm not sure where he is. I ended up in Australia. Let that be a lesson. Oh, okay, this was the slide I was expecting. So this bit is really the processing the instrument. It's taking the instrument out of the data. This bit is doing the science. Doing the science depends on what science you want out of it, and it's pretty much up to you, really, unless you're a member of a big team with a science pipeline already set up. Doing this is probably best left to the people who know the instrument best, which generally means the observatory. So ideally, it would be the observatory does this bit and the scientist does this bit. That may not happen in practice. So the observatory may have a data reduction pipeline that handles the data from their instrument, and you may want to use it, you may not. But if they have, here's a pipeline, here's the obvious picture of a pipe, here's what goes in, data goes in, raw data goes in, processed data comes out, and you can see the various things that go through. If you have an awful lot of data and you want to process it quickly, you can try and set up a parallel pipeline and do all these things in parallel, and if you're lucky you can have really multiple pipelines. Parallelization is one of the keys to getting things to go fast nowadays. When I gave this talk at first, I was trying to find a neater slide to illustrate the idea of parallel processing, and the best I could come up with was this. So, this, it's now dated a bit because I suspect nobody plays this version of Plants vs. Zombies anymore, but you get the general idea. Zombies come in, plants process them, and something happens, and it's all happening in parallel. One of the trickiest things about giving this talk the first time was actually getting this slide without breaking any of the department's rules about the use of IT equipment. Okay, look, no government regulations were broken in the course of this talk. Some may have been bent a twist. I don't know, this didn't really seem to gel with most people last time, but do we have any keen photographers in the audience? Anybody who's got a camera that will take raw data? Ah, right. How many people use it? Ah, right, okay. You're probably going to write your own pipeline.
That's what I'm doing right now, actually.
Right.
Yeah.
Okay. So this is probably the most familiar image processing pipeline around, and most people don't even realise it exists. So every digital camera has a sensor, raw data comes off the sensor. The format of that raw data is really weird and proprietary. It's processed by an amazing bit of electronics, which does it in the time that it takes you to click the shutter. But it's done white balance, it essentially does flat fielding in some cases, it does noise reduction, it does format conversion to JPEG, it does all sorts of things. And if this was a proper photographic talk, I'd explain why you might not want to do that, and you might want to actually use the raw data yourself. But, so, the they that does the work you may want it to be you. If there's a pipeline for the instrument, well, if it's something like 2D FDR, you have to run it for yourself anyway, although you don't write it. You may not trust it, you may want to do it your way, you may have requirements it doesn't meet. It may be in beta, and if it's a new instrument, that's almost certainly the case. If there isn't a pipeline, you have to do it, and you have to do the science processing, probably, unless you're in something like the Galar team and you've got a science pipeline being set up. Okay, now we're on to the last bit. How do they do it? How have I for time? Oh, okay. The way it used to be done tended to be big integrated systems, the IRAFs of this world and so on. Now there's a trend towards it being small do-it-yourself toolkits, usually based around Python. So the 1980s were the heyday of the big systems, the big integrated systems. You had apes in the radio, you had Midas or Midas, depending on which continent you come from ITSO, IRAF still with us, Figaro, which only gets a mention because I wrote it and I like to pretend to myself that some people still use it, Gypsy, which I don't think I've heard of for a very long time. Starlink, which actually still is going. Starlink itself was shut down some time ago, but its software survives and is, in fact, still maintained. Later on, you got bigger systems. There was APES++, which was an attempt at a really big, it was a very ambitious attempt to invent a new system. It came to a sort of grief and lives on mostly as CASA. FACE, F-A-S-E, Future Astronomical Software Environment, is very faint here. It's faint because it was a bright idea about 4 years ago. About 2 years ago, not much had happened, and now I'm just letting it fade slowly away. There doesn't seem to be a lot of, either there isn't a lot of enthusiasm, or there isn't a lot of money for producing these big systems anymore. There are pipelines, things like 2D-FDR, ORAC-DR, which we use for IRIS. ITSO have their common pipeline library for building these things. Increasingly, people are going to build pipelines out of either IRAF scripts or PyRAF scripts nowadays, or just Python itself raw. Out of toolkits so this is the do-it-yourself bit. Python clearly the dominant player at the moment. Python is great for linking together all sorts of things, for sequencing things, for putting together a do-it-yourself package out of really great modules that other people have written. And there are a lot of modules for Python, and that's really where it gets its power from. There's PyRAF, there's AstroPy. If you want to, there's still IDL for people who want to pay for it. There's GDL, which is IDL for nothing, but I haven't heard of anybody using that much. Image displays, if you just want to look at your data in your FITS file, and it may not be a FITS file anymore, it may be an HDF5 file, there are other formats. There's a sort of re-look at FITS now, especially in the light of the data sizes being used. SAO image is the dominant one, I think. ITSO SkyCat. AAO Glimpse, which generated all the nice movies that you didn't get to see just now. But there's also been a great rush recently, a deluge of new FITS image viewers recently. Most have a sort of either web orientation, they're using things like WebGL, JavaScript, or they're particularly aimed at handling 3D data, hyperspectral cubes, RA one way, DEC the other, and wavelength the other way. That's the sort of thing you get out of IFUs. It's what the radio people have dealt with for quite a long time. If you're writing your own stuff in Fortran or C or anything else, the old standby libraries, pgplot for graphics, the almost essential CFITS.io for FITS input-output. It's pretty hard to do without that if you're reading FITS data. Just a quick word about trends at the moment. You've got enormous, super amounts of data and super amounts of processing. You naturally start thinking about supercomputers. Here's G-Star down in Swinburne. Here's Magnus over at the Causey Centre in WA. They've got quite a few, but Magnus is by far the best picture on it. I know absolutely nothing about its scientific capabilities, but it takes a really great picture. Amazon, there's an awful lot of people now starting to use Amazon Web Services, cloud services, that Amazon will store your data for you. They'll sell you processing time on it. So in a lot of cases, your data is no longer coming onto your laptop because your laptop probably doesn't have space for it, and it's being stored somewhere else, which means that there's now a trend towards, the phrase you hear is bringing the computing to the data rather than the other way around. So you have your data over on something like this, you have to get your programs and your processing over to it, which is a completely different sort of problem to the one that we used to have. Now your problem is, how do I get what I've written to work on something like this? And they won't give you root access if you want to try and get it in there. That's actually a problem for some people. Another trend is to get root CPU force for when you do handle things in parallel. a move towards doing things on GPUs, on graphic processing units. Hey, who's got one of these? Right, yes, just about everybody. This is a 15-inch one. They have more powerful GPUs. You people who've got these, you probably haven't opened it up for a while, but if you do, the most powerful chip in there probably isn't the Intel CPU there. It's actually probably the NVIDIA or ATI graphics chip sitting next to it. And that does an amazing amount of parallel computation, parallel floating point computation really quickly. I mean, it's doing every single pixel on this screen is being handled in parallel by a graphics chip in that laptop at the moment. It works best if you're trying to do exactly the same thing to every pixel, and it works best if or pixel of your data, come to that. So it works best if there's exactly the same number of zombies coming down the track and exactly the same number of flowers of the same type of plants waiting for them. And they're also really hard to program, but if you really want speed, that's worth looking at. 3D visualization, I was saying, for hyperspectral data. I picked this one pretty much at random. This is from the Gaia web pages. Gaia is, as I said, Starlink still lives on to some extent. This is still actively being pushed. This will rotate it around nicely, all sorts of clever things. If you really want to get up close and personal with your data, you can fly through it in virtual reality. So this clip is taken from a demo at the ADAS meeting in Sydney last year. And that brings me to ADAS. If you want to know more about what's going on at the cutting edge of things, ADAS, I can never remember what it stands for. It's Astronomical Data Analysis Software and Systems, right? Yes, good. Yearly meetings. It's now up to the 25th. The next one will be the 26th in Trieste. So if anybody wants an excuse for going to Italy at the end of this year, there you are. Book now. That's a good way of finding out what's going on. If you want to find another way of finding out what's out there is ASCL, Astrophysics Source Code Library, is a good place to start if you're trying to find something that does something. So the people at ASCL trawl through the scientific papers and any code that's being used to generate an astronomical paper ought to be in here, and any code that anybody submitted ought to be in here. So that's another thing to take away. If you're looking for something, don't reinvent the wheel. Have a look to see if it's been invented first. If you have to do it yourself, if you do something good, submit it so someone else can find it. And that's all. If the movies had worked, we'd have run over time.
So, any questions for Keith?
Completely dumbfounded. Oh, right.
I just had one thing I thought was nice was your mention of all the flat fields and arc frames and things like this, in correlation with the errors that you can get on CCDs. So this is maybe a reason why for some instrument you might want to request additional calibration frames if you knew that it had one of these problems.
Yeah, you have to think very carefully about how you're going to calibrate this stuff. It's very tempting to shrink, to be cheap on calibration data because it's not science data. It feels like it's time that you could be on the sky. So you want to think about what calibration data you can take before the event, if possible, as well. In twilight or in the afternoon before setting up. And but if things are changing during that, you want to calibrate it well, and you want to calibrate it well. Don't skimp on calibration data. You'll regret it later.
In fact, just talking along those lines, some of the data that I've received, I've noticed that there is pre-science data calibration, taking in science stuff, and then in the middle of all this is another set of calibrations. And another again right at the very end, just to be sure to be sure.
Yeah.
Thorium as well as normal flats.
Well, some places you actually tag a calibration for every image.
Oh, right.
Yeah, so I mean, like
Yeah.
you can.
Yeah, we certainly tend to.
Yeah.
If you look at, I mean, for what the Galar people want to do with Hermes, for instance, they're talking about 10th, 20th of a pixel wavelength accuracy. You're not going to get that unless you're very careful about your arcs. It's supposed to be thermally really stable, but any change in the temperature of the instrument is going to move these things. If nothing else, you want to take those arcs just to make sure that they don't change. And if you find that they have, then you'll be very grateful if you took them.
Any other questions? Yes.
Just a newbie question. What would the twilights be very, very useful for? So if you take dome flats and biases and arcs, what would you use the twilights for?
Oh, a twilight flat field as opposed to a dome flat field.
If you just point off source and get a flat field in the middle.
Yeah, I think it's different. They tend to solve slightly different questions. It depends on how good your dome flat is, for one thing.
Yeah.
I'm probably not the best person to ask this. You want to ask a support astronomer about twilight flats.
We saw an example. Somebody said the flat field wasn't flat, so they showed an image mosaic, and that was probably because of structure in the dome flat or the internal lamp that they were using.
I've actually got something that maybe I'm no expert in it, but certainly in my sort of hobby telescope, I bought one of these electrostatic things. Flat, it's supposed to be a bit the bee's knees, where it's 23 inches by 23 inches, and you point your telescope at it, goes through your filters, and guess what? It's at the UV end, it was actually totally cut off. I couldn't get a proper response when I actually did it, and so after a few phone calls and emails, it turns out that because I didn't supply the actual response, it turns out that the left-hand side of the spectrum was pretty much cut off. So I think with the sky flat, you don't get that. You actually get a much better response from natural source than you would do from maybe an artificial source.
Yeah, if I may just add on to that. Also, with dome flat, you just use a lamp inside the dome, and that your incident lights are not parallel. Whereas for sky flat, your incident lights are parallel. So if you just use a lamp, it's all coming in as a cone, and it doesn't actually spread out evenly across your CCD.
And also keep in mind that your lamp has a profile of its own.
So nothing's perfect, right?
Nope, not even so.
Any other questions before we move on? Okay, so